This presentation provides a summary of VORAGO's patented HARDSIL technology. HARDSIL was developed to improve the robustness of CMOS devices to extreme temperature and radiation effects. By implementing HARDSIL in semiconductor products, it is possible to guarantee operation in the harshest environments. HARDSIL-based products have been in production for many years. The technology was developed and patented in-house and has been licensed to leading global semiconductor companies for use in products that have been used in extreme environments, including the rigorous QMLV qualification for use in space. VORAGO offer a portfolio of SRAM and microcontroller products implemented with HARDSIL, as well as licensing the technology to other semiconductor companies and foundries. One of the major problems facing semiconductor performance is that there are millions of parasitic devices embedded in the silicon. This is an unavoidable consequence of the way that semiconductors are made. In the absence of any external forces, a semiconductor device design should be able to operate normally despite these parasitics. However, if there are the effects of temperature, radiation particles, or noise injected into the system, these parasitics can trigger a state change in a device that can lead to an unwanted and unexpected circuit behavior. This could be manifested as latch-up. HARDSIL was developed to create a mechanism that would harden against these effects. This is a picture of a commercial twin-well CMOS process. The P-well substrate is shown. On the left-hand side is the NMOS transistor with the gate, source and drain. On the right-hand side is the PMOS transistor. The PMOS transistor lives in an N-well that is created in the P-type substrate. A structure like this inherently contains parasitic devices. These are shown as an NPN transistor and a PNP transistor. Also shown is a parasitic resistance in the P-type substrate and in the N-well. The problem arises when there is a charge created on the device that has the effect of switching one of these transistors on. The charge can be deposited due to a particle strike that has an ionizing effect on the silicon through carrier creation at high temperatures, or a voltage transient due to electrical noise. If both transistors are triggered on, a low impedance path between power and ground is created, resulting in latch-up. Latch-up results in an unwanted and unexpected functional behavior that requires a reset or power down event to escape from. It may lead to a catastrophic failure of the device that will damage the part and it will not be possible to recover from. So how does HARDSIL help us? A highly conductive layer compared to the conventional P-type substrate is created under CMOS devices. This layer is known as a buried guard ring. The effect of the buried guard ring is that the parasitic resistances are lowered significantly by 2 orders of magnitude, and this prevents the parasitic transistors from going into forward bias and triggering latch-up. The buried guard ring acts as an electronic charge collection plate to eliminate voltage transients, reduce the circuit's noise floor, and improve the ESD performance. The buried guard ring provides complete immunity to latch-up, and there are 0 known instances of a HARDSIL part ever latching up. Here is an actual photo of the silicon. This is the new VA10800 MCU that was designed to operate in the temperature range from -55 to 200 degrees. It is possible to see the horizontal buried guard ring above the faint light horizontal line, and the vertical buried guard ring can be seen more clearly. The incremental difference of adding HARDSIL to an industry standard CMOS process is 1 to 2 mask steps and 3 implants. It is really not significant in terms of process flow and complexity. There is no impact on yield and performance is not impacted. No unique fab equipment is required to implement HARDSIL. These products are manufactured today at high volume foundries. Using a commercial 130 nanometer CMOS process and the HARDSIL process, 2 sets of latch-up test structures were manufactured and the latch-up characterization testing conducted across a temperature range from 25 to 200 degrees. The latch-up data taken shows the effect of increasing temperature on latch-up trigger current for the 2 samples. On the chart on the left-hand side, latch-up trigger current is plotted against temperature at 1.5 volts. For the commercial process, the trigger current is reduced considerably at higher temperatures. At 200 degrees, the trigger current is lowered by almost 80%. The chart on the right-hand side shows the current voltage curve for the HARDSIL sample shown with a solid line and the commercial sample shown with a dashed line at increasing temperatures. Latch-up is not triggered at any temperature level on the HARDSIL sample, but for the commercial sample, the trigger point and the holding point are reduced as temperature is increased. HARDSIL has never been shown to latch up in any testing to date. The high temperature products in the VORAGO portfolio of MCUs and SRAMs operate from -55 to 200 degrees. There has, however, been a lot of testing conducted at higher temperatures. This board shows an SRAM device that was tested at 250 degrees for 2,500 hours. Unfortunately, after 2,600 hours, the board melted. Fortunately, the SRAM product was still working fine. There were over 125 trillion memory reads without an error, and the current consumption profile was extremely stable during the course of the testing. This chart highlights the range of applications that require robust electronics operation in the harshest of environments. These applications are faced with extreme temperatures and conditions of radiation. It is also worth considering that many conventional applications where the most robust electronics have not historically been required can benefit from the robust operation of the HARDSIL-based products. For example, a system can be optimized if a large, heavy, and expensive cooling system can be reduced on account of the semiconductors that can operate at higher temperatures. Similarly, by using components that can withstand radiation, shielding materials can be lessened. Now that VORAGO offer industry-standard ARM-based microcontrollers and memory products, designers no longer have to use legacy, upscreen devices that are not the best fit solution for an embedded system. For more information on VORAGO products, visit www.voragotech.com.